2 of Physics 2212, and we're going through a line charge of tape. Let's go Introduction, Lab Objective, Computational Model. To analyze the charges and pieces of tape will act on each other if we treat them as line charges opposed to point charges. Of course, last lab we just did points. Do lines this time. Importance. Use principles of charge density, Coulomb's law, and Newton's second law. Same thing we did last time. We're just going to use Coulomb's law a little bit differently and do it over many sections over the infinitesimal distance. All right, so here's the key concepts. It's the same stuff as last time. We're just going to use that Coulomb's law multiple times. Well, I guess many times for the 35 sections I did for my line charge on this tape. Of course, I mean, just as last week, we're going to use F net. That way we can tell the charges on the tape. And we have a different electric force, which will give us different numbers. We're going to compare them to last week as well. So summary of lab one, we take the two pieces of tape, base tape, we tear off the U tape, being that's going to charge the base tape, and that's going to give them a positive charge. We found that out later in the lab when we compared it to a negatively charged pen, but yeah, in this lab we found out it's positive charge. Testing the tapes, we did this by holding it near other pieces, near each other, they repelled each other, and of course for neutral things they made dipoles and then attracted them. That wouldn't really matter on the charge, and we know they're positive because of the pen. Determining base tape charge, same kind of stuff I already went through. You know, when they floated, the way the distance in between them is going to tell us what equilibrium they're at, and whatever distance they're at will tell us, uh, based on the gravity, what electric force had to be present, and we can tell what charge at that distance, and that's how we found out the charge of the first tapes. Assumptions and observations. Each base piece is the same charge. Both pieces were treated as point charges. I'm not going to do that this lab. Go line charges. Uh, they both attracted the charged pen, repelled each other, and began floating, and it was about 0.05 meters or 0.015 meters directly beneath it whenever we did that. That's the D I used in my point charge equation. So here's some of the calculations for that lab. We had You just plug in the D with 0.15. Where I could read these out. The force of gravity was the mass of the tape, which was very small. It was 0.002 kilograms times G. It's going to be the gravity. You take the def net, you get the gravity, uh, subtract by the electric force, and you can solve for Q. When you do solve for Q, you're going to get square root of your square root R squared times FG over K. This ended up giving me a Q of 7 times 10 to the negative ninth coulombs. This equals, well, if you just divide it by the number of electrons, because that's going to be the United charge, you'll end up getting 4.375 times 10 to the 10th. And then donated is just over the area of you see what kind of charge you need to accomplish the positive. All right, so let's see. Let's go through the simulation code. With the E field, we use this. This was where kind of like a lot of our integration went in. This sets up what we're going to do with those many and very small sections. Um, and with the line charge, we do the same thing. We do the axis and we split it up into our n, right? And we set our n over here at 35. All right. So, I mean, this is what it ends up looking like. It's going to be the same, not the same error, but the contributions of each point. This ends up giving us a straight line at the middle once you add them all together. Pretty cool. Modeling tape's line charge. Each tape is assumed to have the same net charge and both uniformly charged along their length. I divided each tape into 35 small sections in glow script, ignored interactions of air resistance and electric forces of charges on the same piece of tape. So like the positives on that one tape, we're going to ignore what it does on the other ones that are on the exact same length. So what if they were a point charge? We did this last lab. It takes more charge on a line charge to push the same force. Therefore, we overestimated. We said it was, or we underestimated really. Last lab we said it was to the negative ninth. It's to the negative 10th in a line when we use the line model. The line charge accounted for significantly more charge, about 2.7 times the charge of the last lab. And why are the calculations different when calculating the line charge that they of the uniform? Why are they different? The different forces. You know, you need a bigger force for the line model than you do a point model. And that's essentially the entire reason why. All right, thank you.